All of our products are tested very extensively. They're tested absolutely primarily for flight safety. They're on fast jet aircraft, and safety is absolutely paramount. This is the Stryker helmet, and this particular one is used in the Typhoon aircraft. It provides the pilot with information that he needs for his mission wherever he turns his head. Things like height and speed and also targeting information. And the way that works is that we have these light-emitting diodes all over the helmet, and in the cockpit we have 3 sensors which are looking at the helmet. The LEDs flash in sequence, the sensors pick up the flashing, and the processing can then calculate which direction the pilot's head is turned. This means in the cockpit that when the pilot is wearing the helmet, we can calculate exactly which direction his head is pointing, and we then position the symbology accordingly. This is not just protecting the pilot's head, it's also a piece of electronic equipment, and that's reflected in the way that we have to test it. The first stage of testing is during the product development, and we have to refine the design and test that it's safe for use. The wind test is what happens when the ejector seat first moves, the canopy comes off the aircraft, the ejector seat moves up its rails, and the first thing that happens is the pilot's head is then exposed to a 600 knot wind blast. We need to test that the helmet doesn't distort in that wind blast. Our early design had a much more curved upper surface, which we actually discovered when he came out into a 600 knot wind was acting as an aerofoil and generating lift, and the forces were far too high to be safe. They would tend to pull his head off. So we redesigned the top surface to be much flatter. We need to test that the helmet itself doesn't interfere with that ejection sequence. We do impact testing to prove that the helmet will achieve one of its primary purposes, which is physically protecting the pilot's head. We have the Faraday Centre on site here at Rochester, which allows us to test the electromagnetic compatibility of all of our products with the environment they have to work in. The Faraday Centre has a number of chambers which provide a controlled electromagnetic environment. We can generate some of the vicious emissions that that the helmet will experience. It has to operate on a fast jet which has a radar. It's a very severe electromagnetic environment. There's a lot of equipment radiating a lot of energy. In manufacturing, there are 3 main elements that need to come together. The physical shape of the helmet. Secondly, we've got the display elements on the inside of the helmet. And thirdly, we've got the head tracking elements on the outside of the helmet. We need to know the precise position of each of the LEDs. So we put the helmet on an optical bench, and we turn it round and we measure in 3-dimensional space the exact location of each LED. The final testing is done in an area called RST, Reliability Shakedown Testing, or locally it's known as shake and bake, where we cool down everything to, for the helmet, about minus 40 degrees Celsius, heat it up to about plus 90 degrees Celsius, and we vibrate it. The purpose of shake and bake is if you look at failures through the life of a product, you get what's called a bathtub curve. So very early on, you get a very high failure rate. That then drops, and through most of its life, it's an extremely low failure rate. And then towards the end of its life, the failure rate goes up, and that's the shape of a bathtub. What we want to do with all of our products is that all of those early failures, we want them to happen on our premises before we deliver the product to the customer.